In section 4.4, we're going to look at equidistant theorems. For the warm-up, what do you think a perpendicular bisector is? Do you think you could sketch one? So we have two words here. We have perpendicular and we have bisector. All right, so to sketch one, I'm just going to start with maybe a triangle. Actually, let's make the triangle look like this. Okay, so perpendicular bisector. Perpendicular means 90 degrees, and bisector means cuts in half. And so if we take a side, so let's just do from AB. To draw the perpendicular bisector, we'd want to be in the middle, and it would want to be perpendicular. So here's an example of a perpendicular bisector. All right. The definition is it's a line that is both perpendicular and bisects a line segment. So perpendicular. And it's going to also bisect. So notice it doesn't have to go through an angle. It can, but it doesn't have to. So it's 90 degrees and it bisects a line segment. There are also two more theorems to add, and this will be what we spend the majority of the time looking at. The equidistant theorem is one of them. It says if 2 points are equidistant, equidistant means the same distance from the endpoints of a segment, then the line connecting those 2 points form the perpendicular bisector of the segment. So let's look at 3 examples. Let's say AC is that line segment. We just make it dotted here. So AC is the line segment. Draw a line connecting B and D. So we're going to try to draw the perpendicular bisector. So here's a line connecting B and D. Oops, did that very well. All right, so that line connects B and D. In order to show that BD is a perpendicular bisector, you have to show that B and D are equidistant using congruent segments to both A and C. So notice A is the same distance from B as C, and you can notice that D is the same distance from A and C. So that would mean that this is a perpendicular bisector. It would do 2 things. It would be perpendicular and it would cut this in half. Okay, so again, you just have to show us the same distance from the endpoints of the line segment. Okay, so let's again draw in a line connecting B and D, and we want to see, is this the perpendicular bisector of AC? So to show that, both points would have to be equidistant from the endpoints. So if you notice, B is the same distance from A and C, D is the same distance from A and C, and so what that means is if we draw on this line right here, that the blue line, BD, is perpendicular and it's the bisector of AC. So we're looking for equidistant things. Here's the last example. Again, we're going to draw in BD, and we want to see, is that the perpendicular bisector of AC? And again, it shows us that A and C are the same distance from B, and A and C are the same distance from D. And so this line right here would be the perpendicular bisector, or the blue line would be the perpendicular bisector of AC. Okay, how do we use that in a proof? So we'll do an example. Given PA is congruent to PB, QA is congruent to QB, prove that PQ is the perpendicular bisector of AB. We're going to use this new equidistant theorem. All right, so let's write our statements and our reasons. All right, so here's what's given. All right, now in the given, we actually have enough information. We have shown that P is the same distance from A and B. Q is the same distance from A and B. So this line, PQ, must be perpendicular and a bisector. Okay, so we'll say that. So step 2 already, PQ is the perpendicular bisector of AB. And the reason, it's the equidistant theorem, which again just says if P and Q are equidistant to the endpoints of the line segment AB, then it's a perpendicular bisector. Okay, so that's the equidistance theorem, same distance from the endpoint. Okay, let's take a look at our last theorem, and there's 2 proofs of that. So this one right here, it's the perpendicular bisector theorem. So let's read that. If a point is on the perpendicular bisector of a segment, so this one is on the perpendicular bisector of the segment, then that point is equidistant from the endpoints of the segment. So this is the converse of the equidistant theorem. So we're switching the order of the hypothesis and conclusion. All right, so let's take a look at what that looks like. So we know that this line, this green line, is the perpendicular bisector. We can see it's perpendicular bisects AB. So we're going to say any point on that line. So I can just put a point anywhere. So I can put a point here. This is the same distance from A as it is to B. Anywhere on the line. So I could do another point, like right here. This point is the same distance as it is from A, or to A, as it is from point B. Okay, so if it's on the perpendicular bisector, by the converse of the equidistant theorem, the perpendicular bisector theorem, it's the same distance from the points. Okay, so let's see what that looks like in a proof. All right, given angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. Prove that AE is a perpendicular bisector of BD. Okay, so let's write up our proofs. Okay, so first we have what's given. Okay, we have congruent angles, and so when you see that congruent base angles, you should think isosceles triangles. So if we look, if the two base angles 1 and 2 are the same, then it means AB is congruent to AD, and if the two purple angles, so 3 and 4 are congruent, it means BC is congruent to CD. All right, so let's write those up. That'll be our next step. So step 2, AB is congruent to AD, and the reason, if the base angles are the same, then the opposite sides are congruent. Okay, and then let's do the same thing for our lower triangle. So step 3, BC is congruent to CD. So we can say if, again, the base angles are congruent, then the sides opposite are congruent. Okay, now we have sides that are the same distance from the endpoints B and D, and so we can say by the equidistant theorem, so again, if we look, AC would be a perpendicular bisector because A is the same distance from B as it is to D, and C is the same distance as it is from B to D. Okay, and that's enough information. So step 4, AE is the perpendicular bisector of BD. And how do we know that? We knew the distances, and so that is the equidistant theorem. Okay, let's do one of the perpendicular bisector theorems. So our last proof for today. Example, AB is congruent to AD. BC is congruent to CD. BC. Show that BE is congruent to ED. So we want to show that these two are the same right here. Okay, so let's show that AE is a perpendicular bisector because A is the same distance as it is from B to D, and same as C. C is the same distance from B to D, so we can show that AE is a perpendicular bisector. And then using the perpendicular bisector theorem, if we have, now that we have a perpendicular bisector, then any points on the line, so then if we take a look at point E right here, this should be the same distance away from the from BD. That's the perpendicular bisector theorem. All right, so let's write that up. Okay, so here we go. We have our statements, our reasons. Okay, so this is given. Okay, step 2, we can already say that AE is the perpendicular bisector of BD, and that was the equidistant theorem. All right, and then step 3, we can say that BE is congruent to DE, and the reason is the perpendicular bisector theorem. which again states now that we have a perpendicular bisector, any 2 points on that line must be equidistant to B and D. So now these are the same distances as well because this is a perpendicular bisector. Okay, so we'll practice that today along with the equidistant theorem.